A and B react together to form an equilibrium mixture. An aqueous solution containing 0.25 moles of A is added to 0.25 moles of B. When equilibrium is reached, the mixture contains 0.015 moles of C. So we've got A add 2B in equilibrium with C. So our ratio is 1 to 2 to 1. Our initial amounts are 0.25 and 0.25, and we won't have any C at the beginning. And then at equilibrium, we've got 0.015. So our change is that this has gone up by 0.015, which means that A must have gone down by the same amount because they're in the same ratio. So 0.235. And then 0.25 has got to be minus 2 lots. So subtract 2 lots of 0.015 because the ratio is 1 to 2. And if we do that on our calculator, we get 0.22. So 0.235 and 0.220. At a different temperature, another equilibrium mixture has got 0.3 moles of A, 0.25 moles of B and 0.02 moles of C in 350 centimetres cubed, or 0.35 decimetres cubed, because moles per decimetre cubed. Calculate the value of the equilibrium constant. Well, remembering that the equilibrium constant is the concentration, so concentration being the square bracket, product C over reactants A, and then we've got 2B, so that becomes B squared. Remember that these are concentrations, so when we put in our numbers, we'll need to divide by the volume. So A is 0.3 over 0.35, and B is 0.25 over 0.35, and then we need to remember to square that one. And then if we put that all into our calculator, we get 0.13. So Kc is 0.13. Then if we think about the units, we've got a concentration term on the top and a concentration squared on the bottom. So if we get rid of a few, we've got 1 over C squared, or C to the minus 2. So it's the units of concentration to the power minus 2. So moles to the minus 1. Moles to the 1 to the minus 2 becomes minus 2. dm minus 3 to the minus 2 becomes dm plus 6. When an excess of water is added to chloroethanol, an equilibrium mixture is formed. An expression for the equilibrium constant K for the reaction under these conditions is given there. Suggest why an expression for K can be written without the concentration of water. Well, we've put the water in excess, and also the other solutions are all solutions, so dissolved in water. So the concentration of water is so large, it is effectively constant. So it doesn't affect the rate. There's not changes happening to it. Distilled water is added to 4.71 grams of chloroethanol to make 50 centimetres cubed of solution and then allowed to reach equilibrium. The equilibrium constant is 37. Calculate the concentration of ClCH2CHOH twice. Okay, so the number of moles is 4.71 divided by 78.5. So we'll work that out first. On your calculator, get 0.06. So the concentration of the chloroethanol, ClCH2CHO, is moles over volume. Make sure you turn that volume into decimetres cubed. 1.2 moles per decimetre cubed. That's actually at the start, so we might not need that. Mixture is allowed to reach equilibrium. Let's just rewrite the expression. So ClCH2CHO in equilibrium with, we've got the water, plus H2O Although remember the water is so large it's effectively constant, we can ignore it. So our ratio is 1 to 1. Our initial amount was 0.06 and we had none of that. And then we're being asked to find out the equilibrium concentration of ClCH2CHOH twice. So this will have gone up by x and this will have gone down by x, so 0.06 minus x. If we were to put those into our expression, case 37 equals, so it was x, but divided by our volume that we don't know, over, or we do know it's 50 centimetres cubed, 0.06 minus x over the volume. We can see that the volumes are going to cancel. So 37 brackets times by 0.06 minus x equals x. 2.22 minus 37x equals x. 2.22 equals 38x. X equals so 2.22 divided by 38, 0.0584. Now x is the moles, so then I would need to do 0.0584 over 50 centimetres cubed. And I'm going to get 1.17 moles per decimetre cubed. Figure 6 shows an incomplete nucleophilic addition mechanism for the reaction of water with chloroethanol. Complete the mechanism by adding 2 curly arrows and all relevant charges and lone pairs. So at this point we've added on the water, it's lost electrons to form the bond, so it's become positive. When we broke the double bond and moved the electrons onto the oxygen, it became negative, and we put a pair of electrons on there. Then what happens is we can see at the next step we've still got the oxygen with the minus, but we've lost this hydrogen from the left hand side and the plus charge. And then if we look to the bottom, we can see that that's gone to fetch that lone pair's gone to fetch that proton and to make that OH. And that would be 2 curly arrows and all the relevant charges and lone pairs. When an excess of water is added to ethanol in a similar nucleophilic addition reaction occurs, it suggests why the reaction is slower. So we haven't got the chlorine on now. So what would be the impact of the chlorine? So Cl is electronegative. Let's just rub that out. Is that going to change our answer? Well, so why the reaction is slower than the reaction in 9.5? The nucleophilic attack that happens in this first step happens because C is delta plus. So the C in the C double bond O is less delta plus in ethanol because alkyl groups have a positive inductive effect, increasing the electron density, not decreasing it. Whereas Cl is electron withdrawing because it's electronegative. So as a result of that, the water is much less likely to attack and the activation energy is higher.